students. Today we start with lecture 9 of Math 303. As per my notes, I start with 12. Fz equal to z square, that is x square minus y square plus 2ixy. You know that how it is? Z is x plus iy and square of it. So it is equal to x square plus 2ixy plus I square y square. Value of I square is minus 1, and though it is x square minus y square plus 2ixy. Now if we compare this with u plus iv, so the value of u is x square minus y square and v is 2xy. This implies ux is 2x and vx is 2y. Differentiation of u, x square goes to 2x and y remains constant, and therefore y square is constant and therefore it does not appear. So for v, 2y is constant and differentiation of x with respect to x will be 1 and therefore it is 2. Now as per the previous theorem, means by Cauchy-Riemann theorem, 1 is f dash z is ux plus ivx, and therefore this is equal to 2x plus I 2y. So if we take 2 in common, that is x plus iy, and that is 2z. And obviously we know that if the function is fz equal to z square, then f dash z is 2z, and this is by the definition of CR equation we get the same answer. In 15, fz is equal to e raised to z. So this is equal to e raised to x plus iy. Therefore this is equal to e raised to x, e raised to iy. So this is equal to e raised to x cos y plus I sin y, and this is equal to e raised to x cos y plus I e raised to x sin y. Now again if we compare with u plus iv, u is e raised to x cos y and v equal to e raised to x sin y. This implies ux is e raised to x cos y and vx equal to e raised to x sin y. U equal to e raised to x cos y, v equal to e raised to x sin y. So if we differentiate u with respect to x, at that time y is constant, therefore cos y is constant, y is constant, therefore sin y is constant, and we know that differentiation of e raised to x is e raised to x, and therefore we have the same answer, ux equal to e raised to x cos y, vx equal to e raised to x sin y. And as per the definition in the previous theorem of Cauchy-Riemann equation, f dash z ux plus ivx, and we put these values here, e raised to x cos y, e raised to x sin y. Now we take e raised to x in common, cos y plus I sin y and obviously this is equal to e raised to x e raised to iy, and therefore e raised to x plus iy, and this is equal to e raised to z. Means differentiation of e raised to z is e raised to z, and we know that by the definition also differentiation of e raised to z is e raised to z. And this is by the procedure or by the definition we found in Cauchy-Riemann equation. Now read the statement of 13th example. Important as an exam point of view, but here we are taking the mathematical approach. It's continuous everywhere, but differentiable only at the origin that we have to prove. So fz equal to z square, obviously if you find the definition it is x square plus y square, because mod z equal to square root of x square plus y square, but we are not taking that part here. But if you find the definition it is x square plus y square. To prove continuity, limit z tends to 0 bar means origin f of z is limit z tends to 0 bar mod z square, and obviously this value equal to 0 all the way, and therefore this function is continuous everywhere, and obviously this value equal to f of 0 bar, and therefore this function is continuous everywhere. Now we wanted to prove that this function is differentiable only at origin. So by definition, f dash z equal to limit delta z tends to 0 f of z plus delta z minus f of z upon delta z. This is equal to limit delta z tends to 0 mod of z plus delta z square minus mod z square divided by delta z. Now we find simplification of these terms. This is equal to limit delta z tends to 0 z plus delta z z plus delta z bar minus z bar upon delta z. You know how we split it, because z bar equal to mod z square, that is definition. Here we can split this bar. In note you have to write one more step there, but I can do it here on the board. So this is equal to limit delta z tends to 0 z bar plus z delta z bar plus delta z bar plus delta z bar minus z bar upon delta z. So both these values are cancelled as they have the same values but in opposite in sign. Now which terms are there? This is equal to limit delta z tends to 0 z delta z bar upon delta z plus z bar plus delta z bar. Now what is z? Z is x plus iy. What is delta z? Delta x plus I delta y. Now delta z tends to 0, means this value tends to 0. And what's about these terms? I think you understand how we find it. Z, both these terms are cancelled. z delta z bar upon delta z. So it is here. Delta z will be cancelled and therefore only z bar there. Delta z will be cancelled and therefore only delta z bar. But now delta z tends to 0 and therefore this term will not be in calculation in the further calculation. So this is equal to what we have minus z plus z bar if delta x equal to 0. Z plus z bar if delta y equal to 0. How it is? Now if delta x 0, then this is delta x 0 means I delta y. What is delta z bar? Minus I delta y. So I delta y minus I delta y will give you the minus sign. But if delta y equal to 0, then this is delta x upon delta x, and so this value equal to 1. Now this function is continuous differentiable whenever both these values are equal. So whenever both these values are equal, z plus z bar equal to minus z plus z bar, and therefore 2 of z equal to 0. This is 2 and this is z. Z bar are equal on both these sides, so we may cancel out them. So it is 2z equal to 0, but 2z equal to 0, that means z equal to 0. This means that this function is differentiable only at origin. Is it clear to you? I think, but if you are doing lots of writing practice and doing all these things by writing, you will understand it is very easy for you. Okay, next one. Okay, dear friends, this is sufficient condition for a function to become analytic. Analytic means differentiable. Fz equal to u plus iv, and if it satisfies shear equations, means ux is vy and uy equal to minus vx. So delta w, as I said earlier in that theorem of shear equation, f of z0 plus delta z minus f of z0 equal to delta u plus I delta v. And now I write this equation from SYDSC. The chapter of differentiation of SYDSC, you used to write there a delta a h b y epsilon rho. If you remember it from SYDSC, I taught you, and the same I repeat it here for the delta v. Means here it is ux delta x, uy delta y, epsilon 1 delta x, epsilon 2 delta y, and for v it is vx delta x, vy delta y, epsilon 3 delta x, epsilon 4 delta y. Here delta x, delta y both tends to 0, and whenever they tends to 0, epsilon 1, epsilon 2, epsilon 3, epsilon 4, all these are tends to 0. And this is definition of differentiation at that. But we are using the notion of that for this sufficient condition. Now I put these values directly here. This is equal to ux delta x plus I at there. Now I convert this equation in ux and vx. Now I convert this equation in ux and in vx. So find the values which are uy there. What is uy? That is minus vx. Vx is okay. What is vy? That is ux. So now we replace this value by this value. So this is equal to ux delta x plus I square minus 1 is there, minus 1 is I square plus epsilon 1 delta x plus epsilon 2 delta y. Now I Vx delta x, this term I is outside there, I am taking inside there, plus I ux delta y plus I epsilon 3 delta x like I epsilon 4 delta y. How I write it? First I convert this equation in ux and in vx. This value is u of y. U of y here it is minus vx. Minus vx is I square vx. Clear? And in this equation it is vy. I convert vy into ux. Yes, it is ux. Now I am taking delta x in common. So what I will count by this? Ux plus ivx delta x, I am taking delta x in common, and in this term I am taking I delta y in common. So what I will have, that is ux plus ivx plus epsilon 1 delta x plus I epsilon 3 delta x plus epsilon 2 plus I epsilon 4 delta y. Epsilon 1 delta x, I epsilon 3 delta x. So I am taking delta x in common. So epsilon 1 plus I epsilon 3 delta x, epsilon 2 I epsilon 4 delta y. Now you find that you can make it common also, ux plus ivx. So what you will have, if we take this term in common, it is delta x plus I delta y. On this side we have delta double or delta omega, what you say. Now delta x plus I delta y, this is delta z. This is delta z. And therefore if we divide all this term, by delta z we have ux plus ivx epsilon 1 I epsilon 3 delta x upon delta z epsilon 2 I epsilon 4 delta y by delta z. Now taking limit delta z tends to 0, you will find all these terms are equal to 0 or very near to 0, and therefore we have ux plus ivx. And here you have one thing is that delta x upon delta z, if you take the mod of that, it will be less than or equal to 1, and in the second one delta y upon delta z, mod of that is less than or equal to 1, and therefore these values are very near to 0, it reaches to 0, and therefore we have these values, and therefore it is a sufficient condition. Now I suggest you all the students that you should write it twice, and after writing all these things you will learn it by your heart, and why I am doing what I am doing, that you will understand after writing. Okay, with this I conclude my lecture here. Thank you very much.